In this video, I want to talk to you a little bit about probability. And to begin our probability discussion, I'm going to talk about probability terms. Now, let me make a couple comments about probability. Many years ago when I first started teaching, probability was a topic that I needed to dive into a little bit deeper because we ended up doing a lot of the calculations. And all the stuff we do in statistics basically finds its way back to the fundamentals of probability. Well, flash forward now, and I am in the 2020s, and we don't do the calculations anymore. The software does it for us. So our general knowledge of probability needs to be less. There needs to be a general understanding, but it doesn't have to go as deep. With that, I want to give you some general ideas in this video. I want to start with some probability terms. And when you think about probability, the classic examples are your flipping coins or rolling dice or basic types of turning over cards and playing cards. And I'm going to talk about some of those things. I'll bring some of those up as I go through this, but then we get some other examples a little bit later. So let's start with the experiment. The experiment is whatever we're doing. It's a process that generates an outcome. And that outcome occurs with uncertainty. If you always get the same conclusion every single time, there is no probability. It's always it's a fact. When there is uncertainty, that's where probability comes into play. We want to know the chance of this happening or that happening. Whatever we're doing, if I'm playing craps in Las Vegas and I'm rolling two dice, a pair of dice, and I'm looking at the outcome, and it's a 5 and a 2, it's a 1 and a 6, it's a 6 and a 1, and whatever, I'm rolling the dice and I'm looking at the up faces on the dice. That's the experiment. If I'm playing poker and somebody deals me, let's say they just deal me a single card to start, it's the process of shuffling the deck and throwing that card down and giving me that single card and taking a look at what the outcome is. Whatever that process is, flipping a coin, it's the actual flip of the coin, letting it land and taking a look at the up face. Whatever the process is, that's called the experiment. And the experiment results in, I'm going to put a couple of these things down here at the same time, at least I think I am. I'm going to try to. No, I'm not. Okay. The process results in outcomes, and those outcomes are called sample points. So when I'm rolling two dice, maybe it's a 5 on the first dice and a 2 on the second dice. If I'm turning over a card, maybe it's the 5 of clubs. If I'm flipping a coin, maybe it's a head. And the sample points are the individual elements of what's called the sample space. And the sample space is just a collection of all of them. So when if you're working with a playing card, a deck of cards has 52 cards. There are 52 sample points in a deck of cards. When I'm rolling those dice and I think of two dice and the combinations, there's 36 outcomes. If a regular die has 1 through 6 as the different faces of the die, you put two of them together. So you got 1 1, 1 2, 1 3, 1 4, 1 5, 1 6, 2 1, and on to 6 5, 6 6. You got 36 different outcomes that are possible when you roll a pair of dice. The game that I was talking about called craps isn't necessarily concerned with what the individual faces are. The game of craps is more or less, and there's some other ways of looking at craps, but the general idea is it's interested in the sum. What's the sum of the dice? Is it 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12? Those are the possible sums. Turns out that the sum of 7 is the most likely. The sum of 2 or 12 is least likely. But the way we define the outcomes, the 1 and the 2, the 3 and the 6, the 4 and the 5, those are individual elements. Those are called sample points. The sample space, again, is just a collection of all of those. An event, which is usually what you're interested in, is an outcome of the experiment. It's also a collection of sample points. So we use the word event to kind of collect together different things. So an event might be getting the ace of clubs when I'm looking at a playing card, or it might be getting a club. And getting a club, well, there's 13 different clubs in a standard deck of cards. An event might be getting the sum of 7 on the dice, whereas the sample points that make up that event would be the 1 and the 6, the 2 and the 5, the 3 and the 4, the 4 and the 3, the 5 and the 2, and the 6 and the 1. The 6 different sample points that result in a sum of 7. Sometimes it's helpful to think in terms of sample points, but most of the time when people ask questions, they ask in terms of event. Think about throwing those two dice. What's the chance that the sum is greater than 5? Well, there's a whole lot of different sample points that result in a sum greater than 5. But the definitions: experiment's the process. Sample point is kind of the most basic, sometimes I define it that way, the most basic type of outcome possible. An event is grouping together sample points, and then the sample space is grouping together all sample points. So those are some basic definitions of probability. All right, let's go on and take a look at a couple different types of events. Union. So a union would be where we're putting events together, and actually the next couple we're putting events together, but how we put them together is important. The union of events A and B is the event that A or B or both occurs. Or being the operative word here. Or A or B or both events occurs. We're going to look at some probability tables in a little bit that I'll give you a pretty good idea of this, but thinking in the craps experiment, you get let's think about it. A better example would be the cards. Think about a deck of playing cards. And let me just quickly explain, because sometimes people don't know what a standard deck of playing cards look like. There's 52 cards in a standard deck of playing cards, and there are 4 what are called suits. There's clubs, there's spades, there's diamonds, and there's hearts. 2 of them are black, 2 of them are red. Each of the 4 suits has 13 cards. They have the numbers 2, 3, 4, 5, 6, 7, 8, 9, 10. There's what's called an ace, so you can think of that maybe as a number 1. So 1 through 10, and then there are 3 different cards that aren't numbers. It's a jack, a queen, and a king. These are sometimes called the face cards because there's actually a picture of a jack, a queen, and a king, and a jack would be like a joker. So there's 13 cards in each of 4 suits, a union. So what's the probability I get an 8 or a black card? Well, when you look at the 8s in a standard playing card deck, there are 4 of them. There's the 8 of hearts, the 8 of spades, the 8 of diamonds, the 8 of clubs. When you look at a black card, there are 2 different suits. And so the OR is going to look at all those different options. It's either an 8 or it's a black card. There's a whole bunch of them. The symbol that we'll see used when we talk about union is A, union B. Now, I won't use symbols. I give you symbols because sometimes when you go to a textbook and look at homework problems, you'll see a symbol. That's the symbol that would be used if you want to find the union, the OR event. The other type of event, the most common type of event, is called the intersection. And the intersection isn't the OR, it's the AND. And so in the example where I just used, black or 8, there's a lot of different things think about all those different black cards, right? There are 13 black clubs, there are 13 black spades, and then you have the 8 of diamonds and the 8 of hearts, which are both red suits. So there are going to be 28 different ways to get an 8 or a black. There's 28 of the 52 cards results in an 8 or a black suit. That's going to be the probability. 26 out of 52 would be the probability. Not 26, 28 out of 52 would be the probability of an 8 or black. Whereas the intersection now, what's the probability I get a black card and it's an 8? Well, there's only 2 of those outcomes, the 8 of spades and the 8 of clubs. So the union would have 28 out of 52 possibilities. The intersection would just have 2 out of the 52 possibilities. And so unions and intersections. And again, when we look at some probability tables in a little bit, we'll take a look at this in an example, and similar to how I'm going to ask. Another type of event that you need to be familiar with, and before I go there, the symbol that we use, I like the U. I always thought statisticians were pretty clever. Look at that, union, let's use a U. And then here's statisticians in a nutshell. We couldn't come up with another symbol for intersection. We're like, we'll just turn the U around, turn it upside down. So that's a symbol you see used for intersection. Again, I don't use symbols a whole lot because no one ever calls me up on the phone and says, hey, Mark, we need to figure out the probability A, upside down U, B. People they use words, and that's how I'm going to ask you questions. What's the probability of this happening? What's the probability of that happening? What's the probability of this and that happening? What's the probability of this or that happening? And you should be able to differentiate between unions and intersection. There's one more I want to talk about on this page. It's called conditional probability. Sometimes we have prior knowledge. Sometimes we know some information. For instance, I might tell you, given that the card is black, what's the probability? It's an 8. Okay, I'm using the same A and B here, right? I'm using the 8, I'm using the black. Given that you know the card is black, well, now I don't really have to consider all 52 cards, do I? Because in a standard playing card deck, if I tell you the card is black, there's only 26. 26 of the cards are black, and if I say given that the card is black, what's the probability that it's an 8? Well, of those 26 cards, 2 of them are 8s. And that's going to be the probability. 2 out of 26. If I change that around, if I change the A and the B around, say, given that the card is an 8, now think about the deck of cards. How many 8s are in the deck? Well, there's the 8 of diamonds, the 8 of hearts, the 8 of spades, the 8 of clubs. There's 4 cards in the deck that are 8. Given that the card is an 8, what's the probability it's black? Now again, depending on your familiarity, some of you guys are probably going nuts. You're thinking, I don't know cards all that well. That's okay. You'll see what we're going to do in a second. But given that the card is an 8, what's the probability it's black? Well, 2 of the 4 cards are black. 2 of the 4 8s are black. So a half, 2 and 4, or 1 and half, or 1/2. That would be the probability. Conditional probability symbol that we use looks like this. We're interested in finding the probability of the first one. It's probability of A. Then we use this vertical line. We read that as given. Given that B has occurred, what's the probability of A? That's kind of the way I would read that. Given that B has occurred, what's the probability of A? And again, the symbols that I'm giving you here are not symbols you're going to see on quizzes or exams or anywhere else. They're just symbols that you may run into if you're doing homework problems from a textbook, or you are searching somewhere and someone's trying to give you a shortened version of a question. You may see symbols like this. But you do need to understand the difference between a union, the ORs, the intersection, the ANDs, and the conditional, where I know this outcome has already occurred. Now, given that that has occurred, what's the probability of this one? All right. Next, we have, the complement. The complement of event A is the event A does not occur. Sometimes it's real easy to talk about it. For instance, the complement, if I flip in coins, I say, oh, the outcome is an A. Well, what's the probability that you don't get an A? The complement, the probability of a head is 1/2. What's the probability you don't get a head? That's the complement of a head would be tail. What's the complement of a red card? A black card. What's the complement of getting an 8? Not getting an 8. The complement of A is just not A. The complement is a simple little idea. It seems like, why would we even need to talk about this? Turns out in probability, sometimes probabilities can get tricky quickly. And sometimes when you're trying to figure out probabilities, it's easier to think about it from the complement approach. And we'll actually use some of this, and we'll talk about this when we do talk about some random variables later. But sometimes rather than trying to figure out the probability you want, you kind of turn it around and think about the probability you don't want, because it turns out the probability of A plus the probability of A complement, not A, is 1. So figuring out the probability of A is tough, but figuring out the probability of its complement is not. You just figure out the probability of the complement and subtract it from 1. And we'll see this in some later things we do. So that's a complement. 2 more for you, and then I'll stop this. Mutually exclusive events. That's a term that we use. If 2 events are mutually exclusive, it means they cannot happen at the same time. So when I'm working with the playing cards, if I turn over a card and I say, all right, one of the outcomes is it's red, another outcome is it's black. Can you get a red and black card on the same card? No. Those are mutually exclusive outcomes. They cannot happen at the same time. Now think about the example I was using. A black card, or getting an 8. Can you get an 8 that's also black? You can. So we say those are not mutually exclusive events. Events are either mutually exclusive, they can't happen, or they're not mutually exclusive, in which case they can happen. Rolling a 7, getting a sum of 7, and getting a 6 on one of the die. They're not mutually exclusive, because you can get a 6 on one of the die and get a 7 at the same time, a 6 and a 1 and a 6, for instance. So those would not be mutually exclusive events. Getting a sum of 3 and rolling a 4. If the 2 die are going to, or 2 dice, pair of dice, are going to sum up the 3, there's no way one of those dice can be a 4. Those are mutually exclusive outcomes. And so that's a mutually exclusive. Independent is when the probability of one event does not change if the second event occurs or not. So for instance, if I was to ask you, if I was to flip a coin and say, hey, what's the chance you get a head here on the first flip? You'd probably tell me it's 1/2. That's what most people would tell me. Well, there's 2 outcomes. One of them's a head, one of them's a tail, so 1/2. That's right. Now, if I said I just flipped a head, what's the probability the next one's a head? you're going to say, well, it's still one half. And if I say, hey, I just flipped three heads in a row, what's the probability the fourth one's a head? You're going to say, well, it's still one half, because in that example, what happened prior doesn't have any effect on what happens in the future. Those are independent outcomes. One flip after the next, those are independent of one another. Now, let's take a look at another example. Think about the playing cards again. Let's say I shuffle the deck and I turn over a card and I ask you, what's the chance it's a heart? And again, if you're following with my little card example, you know that 13 of the 52, or 1 in 4 of the cards, is a heart. So if I ask you what's the chance that that card would be a heart, you would say 1/4. Now if I pick up that card, put it back in the deck, shuffle it up, and say, all right, I'm going to do this experiment again, what's the chance the second card is a heart? It would still be 1/4. And if I pick that card up and put it back in the deck and shuffle again, I say, what's the probability the third one's? It's still 1/4. Again, independent. By replacing the card and starting over, the outcome of the first card, the second card, the third card are completely independent of one another. However, a lot of games, like Texas Hold'em, for instance, they don't do that. They turn a card over and you can see whether it's a heart or not. So let's say the first card is a heart. There was a 1 in 4 chance, or let's use these numbers. There's a 13 in 52 chance that the first card is a heart. Now let's say I'm looking at a heart. Without taking it off the table, leaving it on the table, what's the probability the next card is also a heart? And you say, well, if there's a heart sitting on the table, there's no longer 52 cards in the deck. Now there's only, what, 51, right? And because one of the cards, one of the hearts is already on the table, one of those 13 hearts is already there, the probability of the next one being a heart would be 12 out of the remaining 51 cards. So if a heart is sitting on the table, the probability the second one's a heart, it's not the same probability, it changes. How about if the first card wasn't a heart? Maybe the first card was a club. Now in the deck that remains, in the 51 cards that are still in the deck, 13 of the 51 are hearts. And so the second card, whether it's a heart or not in this scenario, depends upon the first card that was already turned over, because it hasn't been replaced. And so sometimes, I think in an earlier video, I talked about a random sample. And we talked about when you go online, sometimes they'll ask, do you want a sample with replacement or not? And here's the place where it matters. If I'm replacing the card, the second card is independent of the first. If I'm not replacing that first card, if I'm leaving it on the table, then the second card is dependent upon what happened on that first card. Was it, in my example, a heart or not? So independent events are where the probability doesn't change. It doesn't matter what happens with the outcome. Whether it happened or not, the probability stays the same. The flips of the coin. You get a head, the next one's a head is 1/2. You get a tail on the first one, the next one's a head is 1/2. The probability of getting a head on the second flip does not have any change of probability based upon what happened first. So independent and independent, and so you have mutually exclusive and not mutually exclusive. With independent, you have independent, not independent, but we have another name for that. We call them dependent events. And so you have independent and dependent events. So two events are dependent if the probability of one of the events does change based on whether the second event occurs or not. So independent, there's no change. Dependent, there is a change. All right, so I'm almost, what am I, about 18 minutes into this video. I'm going to stop here. I have one. These are really good ideas, these types of events. The probability terms are good stuff, good background to know. I'm not going to do a lot with that, however. So especially if you're like, oh my gosh, I've never played cards in my life, you're going to be fine. I want to show you in the next video how I'm going to ask you to work with probabilities. You're going to be answering questions about probability tables, but I'll do that in the next video. So long.